All right, so we're going to start with 5.4 particle motion. And lucky for you, I forgot to change the bell word. So we'll just skip that. All right. So the important things about particle motion here, you guys, is that we are not going to be dealing with three-dimensional movement. We are not even going to deal with two-dimensional movement. We're just going to deal with like one-dimensional, meaning it just moves along like the x-axis or the y-axis. Okay? So when you have a graph that makes it move like this, that does not necessarily mean that it is moving like in two-dimensional space. Okay? We're going to start that way because it's easier. So as this says, that are moving along the x or y axis. Okay, that's how we start because this is a more complicated concept. Okay? So, even though we're going to have position, velocity, or acceleration of the particle and defined it by functions, the particle is not moving along the function. I'm making a point of this because somebody's still going to do it even though I've made a point of this. Huh? You can read, man. But thank you. All right. So what we're going to do here is we're going to talk about the ideas of velocity, acceleration in terms of position, which I've actually kind of talked to you guys a whole bunch because I use physics as an example, right? Because in physics, you use position time, velocity time, acceleration time graphs all the time, right? And if you have position time, what's the slope of that? The velocity, right? If you have velocity time, what's the slope of that? Acceleration. Right? Now that you know calculus, it's even easier to find that stuff, right? Alrighty. So, let's talk about the average and instantaneous velocity.
Hey, mister, these two are tardy.
Woo.
No, mister,
Super tardy.
If you want, you can call in the office.
Why do I want to call the office? That's weird.
Do not give us a time.
I'm still giving you a tardy, dude. Anyways, alright. So, average and instantaneous. We kind of have already talked about this because, of course, mean value theorem literally relates these two things. Boys, if you come in late and start interrupting, I'm going to kick you out. Okay? So the average velocity was when we did the secant lines, right? So this is like the position at A minus the position at B over A minus B. And this is where P of T is the position. Now, do I have to write it in that exact way, or could I write it slightly different? I could write it slightly different. I could go PB minus PA over B minus A. It does not matter which way you do it as long as it's consistent. Okay? And realistically, most of the time, you probably will go PB minus PA over B minus A. So you can do either way. All right. Now, if we want instantaneous velocity, what is that? The other part of mean value theorem, what?
At a moment.
Is at an instant, like at a moment. So that is the derivative. That's how we describe that. The derivative is a split moment in time. So, if we have a particle's position given by a function, like this one here, where P of T is measured in centimeters and T is measured in seconds, answer the following questions. What is the average velocity on the interval from 1 to 3? Well, the average was where we just literally plugged it in and kind of did a secant line. So, let's go P of 3 minus P of 1 over 3 minus 1, right? Well, what's that going to be? Well, I need to actually plug it in. So that's going to be e to the power of 3 times sine of 3. Can I do that in my head?
No.
No, right? And then e to the power of 1 times sine of 1. Can't do that one in my head either. I can do the bottom. It's 2. So then we just need to put that into our calculators, which we can do. Am I the only one doing it? Or Desmos it. That's true. You could Desmos it. E cubed times sine of 3 minus e sine of 1. What do you need to make sure your calculator's in case you're in physics too? Radians. Good. Oh, I was like, wait. There we go. I forgot to divide it by 2. And so this should be 0.274, right? 3.5, 5 rounds up to 4. And this was in centimeters per second. So the velocity of our particle, right, is moving at 0.274 centimeters per second. You all right there, buddy? I think Pablo's gone crazy.
Hey, sir.
Yeah.
Do we know when it's squared or not?
How do you know if it's squared or not?
Alright.
There's two ways. One is we can look at the rate. So here we're doing centimeters and seconds. So that would just be centimeters per second, much like kilometers per hour if you're driving. If you already have a rate, like one of the problems we did yesterday, where you have a rate and you take the derivative, then your rate is already going to be like centimeters per second. So the derivative is centimeters per second squared. The easy way in this unit is just think about what it is. Position is just centimeters. Velocity is, or distance. Velocity is going to be that distance divided by time. And then the acceleration is going to be distance divided by time squared. Okay, and it'll be different depending on your units. In this case, centimeters and seconds. Could be meters and seconds, kilometers and hours, whatever. Okay? Does that make sense?
Yes.
Cool. All right, what is the instantaneous velocity when the particle is 1.5? All right, so this time I actually need to write down my equation, which was P of t equals e to the t sine t. So if I'm trying to find the instantaneous, I need to find the derivative, because I'm going to need to find P prime of t. What rule do I need to do here? Product rule. E to the power of t. Yep, exactly. Product with exponential. And technically even a chain rule, but we're not going to worry about it because it's times 1. But yeah, so e to the t sine t plus e to the t cos t. And so then if I want to find P prime of 1.5, I just need to plug that in and put that in my calculator. Yep. Yep. So this would be 4.787 centimeters per second. I'm not going to lie to you. I did that earlier, so I didn't have to do it. But if you want to punch in your calculator, you can double check it. All right. And again, this is velocity, so it should be centimeters per second. Nope, that's acceleration. The derivative of an exponential is the derivative of the exponent, which is in this case is 1, times the original exponent, like our exponential, times the natural logarithm of the base. But in this case, the natural logarithm of e is 1. So this, interestingly enough, the derivative of e to the t is just e to the t.
Okay, thank you.
It never changes. Yeah, no worries. All right, can we keep going, or do we need another second? Matthias, what's up? Matthias, what's up? Okay. So we can keep going. Excellent. All right. Before we continue, we need to make a connection. Okay. How did we find the slope of a secant line on the interval from A to B? Say what? I just didn't hear you. Huh? Yeah, delta y over delta x, right? So it was just like the slope of the secant. So it was delta y over delta x, which when we expand it is, of course, f of b minus f of a over b minus a, which in our case here is p of b minus p of a over b minus a. And you'll notice I purposely wrote it in the opposite order than last time because I want you to see you can do both. And this is, of course, our average velocity. Okay? In terms of the position of the particle, the slope of the secant line is that average velocity. And then the instantaneous velocity, this is where it's just going to be like, it would be f prime of c. Well, let's back that up a little bit. Let's say that t equals c, therefore f prime of c is equal to p prime of c, which is equal to our instantaneous velocity. Instantaneous, that's a long word, man, velocity. Awesome. All right. So, didn't I already write this? Average and, oh no, this is acceleration. I was like, didn't I write this already? All right, so average acceleration. This is going to be the same idea, the secant line, except that this time it's the secant of the velocity graph. So instead of being P of A and B, it's going to be V of A and B. So V of A, or V of B, minus V of A over B minus A, right? And in this case, this is because or we could say like where v of t is equal to p prime of t, which really is like our velocity function, right? And then our instantaneous is just going to be the same idea as before. It's the derivative, but this time it's the derivative of, I guess we kind of need to do it the way we did it last time. So if we said like t equals c, then it would be v of c, which is also equal to p prime of c, right? These two things are the same. Oh no, hang on. I did that wrong. V prime of c, which is p double prime, which would be equal to our acceleration function. Do you see how all three of those things would be equal? No? No? All right, so if I have the position and I take the derivative, I'd get my velocity. If I take the derivative of the velocity function, I would get acceleration. Or if I took the position and took the second derivative, I would get acceleration. That's what it means. Does that make a little more sense? Yeah, perfect. Okay. I guess I could have done it with T's instead of C, but whatever, I made it C. Just for fun. It wasn't necessary. All right. Particle's position is given by that same function. And let's find the average acceleration. So that means that I'm going to need to this time find v of 3 minus v of 1 over 3 minus 1. But I got a problem. I don't know what the velocity is. Just kidding, we did it earlier. Remember, p of t is equal to v of t, and we did it earlier. What was it? Do you remember?
Why p prime of t equals
Because the derivative of the position is the velocity.
oh,
Okay? And if you remember, it was just et sine t plus et cos t. Right? We did it already in the previous question. Okay. So then we're going to have to go ahead and plug these in, right? So we're going to do like e to the power of 3 times sine of 3 plus e to the 3 cos of 3. So in other words, we got to punch v of 3 and v of 1 into these two equations. We're going to do it on a calculator. And it's going to be over 2. Actually, let's just do the whole thing, which again I did earlier for us. Negative 10.403 centimeters per its acceleration, so seconds squared. If you don't believe me, you can put it in your calculator later. I know, in order to save time and make sure you guys have more time to do practice problems, I did it.
is there you plug in like you did equation of the derivative?
Yep, I did. Exactly. I did this. I plugged in 3, and then I subtracted this equation at 1. Yeah, that's what I did. And then I divided it by 2, because it's over 3 minus 1. Yeah, so all I did is I just plugged these into this equation. Okay? All right, instantaneous acceleration. Well, that means I'm going to have to take my, like this is the p double prime of t.
I have a question.
Yep, what's up?
Like the question we did before, it's asking us to find the acceleration, but you said that position prime is equal to velocity,
Yep.
but it's asking us to find the acceleration.
When? Here?
No, that
Here?
is acceleration or velocity.
Because here I wrote down what the velocity, I found the velocity function, because I'm using the velocity function to find my average acceleration. When I'm doing the acceleration, the instantaneous, I have to actually find the derivative. So what I'm going to do here is I'm going to write out what this was. And then I'm going to have to take the derivative of this to find v prime, because v prime of t is equal to my acceleration of t. And so, interestingly enough, it's just going to kind of get bigger. E of t sine t plus the derivative of sine, which is cosine, plus the derivative of et. So here, maybe I'll show you like what we're doing. So this part, oops. Why is it not highlighting? Weird. Oh, because it's text highlighter. I want freehand. So the derivative of this is all that part. Okay, now I'm going to take the derivative of et cos t. So it'd be e to the power of t, which is the derivative of et, times cos t.
As an assignment only for students who class.
Don't worry about it yet.
We're gonna
All right. What is the instantaneous acceleration of this thing? We were doing that. So we did the first part, which is e of t derivative, which is et, cos t. And then we need to go ahead and add the first function times the derivative of the second, which is negative sine. I'm going to move that negative out front here. So instead of being plus, I'm going to do it like that. All right, now that is the derivative of this part. And we got some stuff that simplifies. Because et sine t and minus et sine t goes away, and these two can be combined. So my acceleration function is going to be 2e to the power of t cosine of t. And then I just need to plug in my values, so a of 1.5, and then I plug it into this function, which I did already for us, is 0.634 centimeters per second squared. Good? Questions, or are we loving this? We're hating it. Why do you hate it? You don't understand.
I have no clue what it is.
Well, I'm sorry.
I'm just writing, but not like actually there.
Part-time Paulina. Gotta get part-time Paulina's brain on.
When is the break?
Yeah, we will. All right. So let's just write down and like summarize what we kind of did here. So we did that P of t is the position. V of t, or P prime of t, is the velocity. And A of t, or V prime of t, or P double prime of t, is the acceleration. Amazing, right? So we've already done this. We've already compared the derivatives with the originals, etc. But let's do it when we're specifically talking about position and velocity now. You wrote down like 3 words, ladies. It's only 3 words. Okay, fine. All right, yeah. So the position is P of t. The velocity is V of t or P prime of t. So if the velocity is 0 or undefined, what's going on with the position? It may have a critical point, which would mean it may turn around. It may switch directions. Doesn't have to, but it could. If it is positive, that would mean that it is increasing. If we think about vectors from physics, what does it mean if it's increasing? What are the 2 directions it's going? Right or up? So it's moving right or up, depending on which axis we're on. If it's negative, it's the same idea, except that it's going to move left or down. Sure, it's decreasing, but that's not like, what does decreasing mean in terms of vectors? Well, it's going down or left, right? All right, what about if it changes from positive to negative? That'd be like a maximum. If it's changing from negative to positive, that'd be a minimum, but it doesn't actually matter. What is it actually doing? Look at the first one we did. What is this actually doing? So if it moves from one direction to the other, that means that this is turning around. So the motion of the particle, if we have a critical point, is that it changes direction. It was going right, it stops and goes left. Why doesn't that make sense? Sure it does, come on. You've taken physics. You've taken it. I mean, you may not have understood it. I purposely paused it before saying that. Okay, so let's talk about acceleration and velocity then. So we already know our velocity is like V of t or P prime of t. For acceleration, yes. So this is going to be A of t, or it could be V prime, or it could be P double prime. That's our acceleration. Now, if the acceleration is 0, that means that we have a potential, because remember, it always is potential. So it's a potential change in velocity. Okay? If it is, if the acceleration is positive, that means the velocity has to be increasing. And if the acceleration is negative, the velocity is decreasing. Now, I'm going to lie to you in a second, because that's what we do in like physics. Hello. Claro que sí. All right, now, if the acceleration changes from positive to negative, that means that the velocity is going to change like this. So this one is kind of the same as what we've done before, right? And if the acceleration changes to negative, positive, the velocity will. What does that really mean? Like, I almost feel like I shouldn't have even put this in there. Yeah, but I'm going to explain it with things that are not on there. Basically, all of this part here has caveats in it. Because what it means is that if the acceleration is, say, moving to the right, and the velocity is moving to the right, what happens to the particle? It accelerates and it speeds up. What happens if the acceleration is to the left and the particle is moving to the right?
It's slowing down.
It slows it down, right? So if the acceleration and velocity are in opposite directions, then it's going to slow down. So here when I say it's increasing, it's going to be increasing if my velocity is also positive. And it's going to be decreasing if the velocity is the opposite. So what's kind of awkward here, so in this case it's like if the velocity is positive, right? Because the acceleration is negative. It's awkward. So like that's why I said like there's a huge caveat here. I almost like shouldn't even put it there. Because we need to be able to say like, well, when the acceleration is positive, velocity is either increasing or decreasing depending on the direction. Okay? So let's add this caveat down here. So if acceleration, guys, I know you're saying you don't understand, but that probably just means you're not listening.
Oh, yes, yes.
It's a very simple thing. Like if acceleration and velocity are the same sign, it speeds up. Okay? It speeds up. And if they're opposite, if the acceleration and velocity are opposite signs, then it slows down. Okay. This one, probably more helpful. This chart, honestly, less helpful because there's caveats in it, right? It matters the direction of things. So, let's then talk about, whoa, sorry. Well, yeah, that was very whiny. Nah, girl, it's there. You can look it up later. Hey. Oh, you have it? Okay, can you show me a window? Because I'm still teaching. No, but I gotta finish teaching these guys, man. All right, so applying this, the graph below represents the position S of t of a particle, which is moving along the x-axis. Therefore, the particle's not doing what? What is it not moving along? The graph, or the y-axis, yes. It is only moving along the x. What this does is simply tell us what's going on, okay? So, S of t is our position. Right? So our S of t is equal to P of t as we were calling it earlier, right? Earlier I was calling it P of t. So don't be confused just because we decided to call it S of t. It's still the position, right? It tells us it's the position. Alrighty. At which point is the velocity equal to 0? Well, this is when we have a max or a min, right? So it's going to happen at B and D. And this is because S of t has relative extrema. At which point is the acceleration equal to 0? I think it's just 1. All right.
What does B?
We are all wrong so far, but also partially right. So what is the common thing? Yes, C is the common thing you're all trying to tell me, right? Why is it C?
Because it's an inflection point.
Exactly. And the inflection point is when the second derivative equals 0, right? So when it changes from concave down to concave up, that means the second derivative is 0. So that's where the acceleration is going to be nothing. It's 0, okay? So that is because S of t has a point of inflection, or poi. Poi. Alrighty. On what interval is the particle's velocity positive? Let's start by doing our justification this time. So what would be our justification?
That is right or up. From
Sorry, not V of t, it should be S of t.
Graph is increasing.
moving right.
Because S of t is increasing, yes. If the position is increasing, that would mean that it has to have a positive velocity, right?
And E.
So that's going to happen, well, we're doing the intervals this time, right? So from, yeah, negative infinity to B, and then from D to infinity. That doesn't make sense. We can't do negative infinity. So what would we actually, because if this is time, what would we need it to be?
0.
0. Exactly. So it should be from 0 to, what was it, B at the top? And then from D, we could technically say infinity this time, although it's unlikely that this thing just keeps moving forever, right? But we could still say that because they haven't given us a stop time for it, okay? All right, when is the velocity negative? Well, same thing. Let's start with that whole S of t is decreasing, exactly. Which means that this time it's going to happen from B to D. Anywhere else? Oh, and I guess here we should probably say what it was. V of t was positive, and V of t was negative. Where is the particle's acceleration positive? So again, let's start with the reasoning. So this is going to happen because S of t is what? Concave up or down? Up. So it is concave up. So therefore, that's going to happen from C to infinity. So this is A of t is positive from C to infinity. And it's going to be, the acceleration will be negative when S of t is concave down. Now this time it's not infinity. What do we got to say?
0.
Yes. So this time it's going to be from 0 to C. Is that all making sense? No, it's not? Well, crap. All right, so we're going to do the 5 commandments of particle motion. Yes, I'm aware that's a little sacrilegious. We're still going to do it. 5 commandments of particle motion.
Oh my god.
Stop making me repeat it. You're trying to get me canceled. Okay,
Can I cancel? Is that okay?
I'm sure you already have. If velocity is greater than 0, the particle moves right. I've already talked about it, but we're going to write them down to make sure we know this. So then what would be number 2?
If it's less than 0, it moves left.
Yeah, if velocity is less than 0, the particle moves left. I guess maybe we should add to this though. Right or up, and left or down, right? It would technically be those 2 things. Okay. Number 3. Speed is increasing when velocity and acceleration have the same sign. I don't know why I made number 4 so big. I should have made these all a lot smaller. Oh well. And then speed is decreasing when velocity and acceleration have different signs. Right? So it's literally like same sign, faster. If that doesn't make sense to you, I can push someone around. Yeah? Okay, perfect. We're going to pause. So the last commandment that we need is if the velocity equals 0, but the acceleration is not 0, then the particle is momentarily stopped and is changing directions. So I want you to think about what that says, and hopefully it makes sense.
It's like concavity, no? So
Yeah.
now it gets to 0 and then changes sign.
So
Yeah.
now in that case, there is an absolute or a relative maximum.
Yes, exactly. Because if the velocity is 0, there has to be that max or min in the position. And if the acceleration is not 0, it's not an inflection point. So yes, that's correct. All right, so let's do this last question.
Wait.
Oh, sorry. All right. Yes?
Yes, sir.
All right. So suppose the velocity of a particle is given by the function v of t is equal to that. For t is greater than 0, which is pretty much always what we're going to do, because t being less than 0 would mean we have to go back in time. Okay? Where t is measured in minutes and v of t is measured in inches per minute. Find the values of v3 and v prime of 3. So if I'm asking for v of 3 and v prime, what am I really asking for? The velocity and the acceleration, because that'll let me figure out what?
Position at a time.
The speed, whether it's speeding up or slowing down, right? That's what we were just talking about. So that's why then it says based on these values, describe the speed. Okay, so v of 3 means I'm just going to plug it into here. So that's going to be what? 5 and 7, 7 squared, 49 times 5, 300 and, no,
Decibels.
50 times 5, 245.
So it's 5 times 245.
And that'll be in inches per minute. My mental math almost failed me there. Then for the derivative, well, we need to find that first. So v of t. Probably in this case, it's easiest to just do the product rule. So the derivative of the first is 1 times t plus 4 squared, plus the first term times the second term squared, which is a chain rule, but it's a really easy chain rule because the derivative of the inside is 1. So it's just that, okay? So then I'm going to plug in 3 into that. What am I going to get here? I'll get 49 plus 5 times 2 times 7. So I get 49 plus 70. And so v prime of 3 is equal to 119 inches per minute squared. Now, really, it didn't even necessarily matter once I knew it was positive. That's the important thing. So what's going on? Well, v of 3, that's an ugly 3, is positive, and a of 3 is positive, so the particle is speeding up. Now, let's be more specific. Speeding up how or where?
To the right.
I love it. Look at you guys knowing your physics. I'm going to have to go and give, like, Mr. Landry a pat on the back. Wow, that was rude. This is on video, girl. You better hope he doesn't watch that.
Why would you like to watch it?
Oh my gosh.
That's why you should have a vote.
Okay. On what interval is the particle moving to the left, right, show your analysis, justify your answer? So if we want to know when it's moving to one direction or the other, I need the critical points of the velocity, which means I need the acceleration to be 0, right? Say what? Yeah. Oh wait, sorry. No, we're talking about moving. I apologize. Moving, not the velocity. So it's when it's moving right or left. So we need the velocity to be 0. I apologize. So we need v of t to be 0. Okay? So that means I need this thing up here to be 0. That's going to happen.
When it's 0.
No, that's the acceleration. That's why it's hard. I was like, it should be up here. -2, -4. There we go.
When they are 0.
So this is going to happen at -2 and -4. Oh, sorry. It equals 0 when t equals these. Do those help us?
What?
Why wouldn't they?
Well, they're outside.
Because they're outside our thingy. Yes.
This means that the only time the velocity was 0 is like in the past. So we don't care. Which means that technically if we wanted to do this, like, you know, we're going to start at 0. We have no critical point, so we could just plug in 1. We're going to get positive and positive. So it's therefore always moving right. So it is always moving right. If you wanted to and write it as an interval, it would be from 0 to infinity. Okay?
Let's write